Hi, hello there. Welcome to Network Virtualization. So imagine you live in a two-bedroom house. You use the second bedroom for storage. The second bedroom is packed full of boxes, but you still have more to place in the storage. So you should consider building an addition on your house. It would be costly endeavor, and you may not need that much space forever. So you decide to rent a storage unit for the overflow. So similar to a storage unit, network virtualization and cloud services can provide a business with options other than adding servers into their own data center. In addition to storage, it offers other advantages. So get started with this module to learn more about what virtualization and cloud services can do. So on this video lecture, we will be talking about network virtualization, and the module objective is to explain the purpose and characteristics of network virtualization. So along with this, we will be talking about the cloud computing, virtualization, the virtual network infrastructure, the software-defined networking, and the controllers. So let's start with cloud computing. So cloud computing involves large numbers of computers connected to a network that can be physically located anywhere. So providers rely heavily on virtualization to deliver their cloud computing services. So cloud computing services can reduce operational costs by using resources more efficiently. So cloud computing addresses a variety of data management issues, like it enables access to organizational data anywhere and at any time. Next is it streamlines the organization's IT operations by subscribing only to needed services. Okay? Next is it eliminates or reduces the need for on-site IT equipment, maintenance, and management. Also, it reduces cost of equipment, energy, physical plant requirements, and personal training needs. And the last one is it enables rapid responses to increasing data volume requirements. So cloud computing, with its pay-as-you-go model, allows organizations to treat computing and storage expenses more as utility rather than investing in the infrastructure. So capital expenditures are transformed into operating expenditures. Okay, so let's talk about cloud services now. So cloud services are available in a variety of options, tailored to meet customer requirements. The three main cloud computing services defined by the National Institute of Standards and Technology, or NIST, in their special publication 800-145 are as follows. Okay, so the first one is Software as a Service, or SaaS. Okay, so the cloud provider is responsible for access to applications and services such as email, communication, and Office 365 that are delivered over the internet. So the user does not manage any aspect of the cloud services except for limited user-specific application settings. So the user only needs to provide their data. Okay? So the next one is Platform as a Service, or PaaS. So the cloud provider is responsible for providing user access to the development tools and services used to deliver the applications. The users are typically programmers and may have control over the configuration settings of the cloud provider's application hosting environment. Next is Infrastructure as a Service. Okay? Infrastructure as a Service, or IaaS, the cloud provider is responsible for giving IT managers access to network equipment, virtualized network services, and supporting network infrastructure. So using this cloud service allows our IT manager to deploy and run software code, which can include operating systems and applications. All right. So cloud service providers have extended this model to also provide an IT support to each of the cloud computing services. And what we have here is, of course, the IT as a service, or ITaaS. Okay. So for businesses, ITaaS can extend the capability of network without requiring investment in new infrastructure, training new personnel, or licensing new software. So these services are available on demand and delivered economically to any device anywhere in the world without compromising security or function. Okay, next is cloud models. Okay, so there are four cloud models as shown in the figure here. You've got hybrid, public, private, and community. Okay, so public clouds. Okay, let's start with public clouds. Public clouds are cloud-based applications and services offered in public cloud that are made available to the general population. So services may be free or are offered on a pay-per-use model, such as paying for online storage. Okay, so the public cloud uses the internet to provide services. So the next one is private cloud. Okay, so cloud-based applications and services offered in private cloud are intended for a specific organization or entity, such as the government. A private cloud can set up using the organization's private network. So through this can be expensive to build, okay, and maintain. So a private cloud can also be managed by an outside organization with strict access security. Next, third one is the hybrid cloud. Okay, so a hybrid cloud is made up of two or more clouds. Example, part private and part public. So where each part remains a separate object, but both are connected using a single architecture. So individuals on a hybrid cloud would be able to have degrees of access, okay, so to various services based on the user access rights. All right, and the last one is the community clouds. So a community cloud is created for exclusive use by a specific community. So the differences between public clouds and community clouds are the functional needs that have been customized for the community. For example, healthcare. Okay, healthcare organizations must remain compliant with policies and laws. Example, the HIPAA that requires special authentication and confidentiality. Right? Next, cloud computing versus data center. Okay, so the term data center and cloud computing are often used incorrectly. Okay, so these are the correct definitions of data center and cloud computing. So data center, okay, so typically an off-premise or a data storage and processing facility run by an in-house IT department or list offsite. So that is a data center. When you say cloud computing, so typically this is an off-premise service that offers an on-demand access to a shared pool of configurable computing resources. So these resources can be rapidly provisioned and released with minimal management effort. So data centers are the physical facilities that provide the compute, network, and storage needs of cloud computing services, while cloud service providers use data centers to host their cloud services and cloud-based resources. All right? Let's talk about virtualization now. Okay, so cloud computing and virtualization. What's the difference? So in the previous topic, you learned about cloud services and cloud models. So this topic will explain virtualization. So the terms cloud computing and virtualization are often used interchangeably. However, they mean different things. All right? So virtualization is the foundation of cloud computing. Without it, cloud computing, as it is most widely implemented, would not be possible. So virtualization separates the operating systems or OS from the hardware. So various providers offer virtual cloud services that can dynamically provision servers as required. For example, Amazon Web Services or AWS provides a simple way for customers to dynamically provision the compute resources they need. These virtualized instances of servers are created on demand. Okay, so as shown in the figure here, all right, so the network administrator can deploy a variety of services from the AWS Management Console, including virtual machines, web applications, virtual servers, and connections to IoT devices. All right. Okay, let's talk about dedicated servers now. So to fully appreciate virtualization, it is first necessary to understand some of the history of the server technology. So historically, enterprise servers consisted of a server OS such as Windows Server or Linux Server, okay, installed on the specific hardware as shown in the figure. So all of the server's RAM, processing power, and hard disk drive spaces were dedicated to the service provided, example, web, email, or email services, and others. So the major problem with this configuration is that when a component fails, the service that is provided by that server becomes unavailable. So this is known as a single point of failure. Another problem was that dedicated servers were underused. All right? So dedicated servers can often sat idle for long periods of time. So waiting until there was a need to deliver the specific service that they provide. So these servers wasted energy and took up more space than was warranted by the amount of service provided. This is known as the server sprawl. All right, so next is virtualization or server virtualization. So server virtualization takes advantage of idle resources and consolidates the number of required servers. So this also allows for multiple operating systems to exist on a single hardware platform. For example, in the figure, the previous 8 dedicated servers have been consolidated into 2 servers using hypervisors to support multiple virtual instances of the operating systems. The use of virtualization normally includes redundancy to protect from a single point of failure. So redundancy can be implemented in different ways. If the hypervisor fails, the virtual machine can be restarted on another hypervisor. Also, the same VM can run on 2 hypervisors concurrently, so copying the RAM and CPU instructions between them. So if one hypervisor fails, the virtual machine continues running on another hypervisor. Okay? So the services running on the VMs are also virtual and can be dynamically installed or uninstalled as needed. So the hypervisor is a program or firmware or hardware that adds an abstraction layer, okay, on top of the physical hardware. So the abstraction layer is used to create a virtual machines which have access to all the hardware of the physical machines such as CPUs, memory, disk controllers, and network interface cards. So each of these virtual machines runs on a consolidated number of servers they require. For example, it is not uncommon for 100 physical servers to be consolidated as virtual machines on top of 10 physical servers that are using hypervisors. Okay, so let's talk about the advantages of virtualization now. So one major advantage of virtualization is overall reduced cost. So you've got less equipment is required, less energy is consumed, and less space is required. Okay, now with less equipment is required, virtualization enables server consolidation, which requires fewer physical servers, fewer networking devices, and less supporting infrastructure. So it means lower maintenance cost. So the next one is less energy is consumed. So consolidating servers lowers the monthly power and cooling costs. So reduced consumption helps enterprises to achieve a smaller carbon footprint. Okay? When you say less space is required, server consolidation with virtualization reduces the overall footprint of the data center. So fewer servers, network devices, and racks reduce the amount of the required floor spaces. Okay? So there are additional benefits of virtualization. So like easier prototyping. So self-contained labs operating on isolated networks can be rapidly created for testing and prototyping network deployments. So if a mistake is made, an administrator can simply revert to a previous version. So the testing environment can be online, but isolated from the end users. So when testing is completed, the servers and systems can be deployed to the end servers and end users. Okay? The next one is faster server provisioning. So creating a virtual server is far faster than provisioning a physical server. Okay? Next is increased server uptime. Most server utilization or virtualization platforms now offer advanced redundant fault tolerance features such as live migration, storage migration, high availability, and distributed resource scheduling. Okay? So next additional benefits would be improved disaster recovery. So virtualization offers advanced business continuity solutions. So it provides hardware abstraction capability so that the recovery site no longer needs to have hardware that is identical to the hardware in the production environment. So most enterprises or enterprise server virtualization platform also have software that can help test and automate the failover over or before a disaster does happen. Okay, so the last one is legacy support. So virtualization can extend the life of OSS and application, providing more time for organization to migrate to newer solutions. Okay, now let's talk about abstraction layers. Okay, so to help explain how virtualization works, it helps to use layers of abstraction in computer architecture. So a computer system consists of the following abstraction layers as illustrated here. So you've got hardware, which includes CPU, memory, NIC, and disk or hard disk storage. You've got firmware or ROM, okay, the operating systems or OS, and the services like web, email, and file service. Okay, so at each of these layers of abstraction, some type of programming code is used as an interface between the layer below the layer above. Okay, so that is between the layer below and the layer above. So for example, the C programming language is often used to program the firmware that accesses the hardware. So an example of virtualization is shown in the figure. Okay, so a hypervisor is installed between the firmware, okay, and the OS. Okay, so the hypervisor can support multiple instances of OSS like what you see here in the diagram. Okay, so this hypervisor has 3 OSS running on top of it. So that means we could have multiple OSS running and each OS could run its own service. All right. Next, let's talk about type 2 hypervisors. So a type 2 hypervisor is software that creates and runs virtual machine instances. So the computer on which a hypervisor is supporting one or more VMs is a host machine. So type 2 hypervisors are also called hosted hypervisors. This is because the hypervisor is installed on top of the existing operating systems, such as macOS, Windows, or Linux. Then, one or more additional OS instances are installed on top of the hypervisor, as shown here in the diagram. Okay, so for instance, we have here a single host. Okay, so definitely we have the shared resources or hardware, and then we have what you call the host operating system. Okay, on top of this host operating system, we have a hypervisor running, which is hosting different OSS on top of it. Now, in this example, we are running 3 virtual machines powered by Windows OS, Linux OS, and the Unix OSS. Okay, so the big advantage of a Type 2 hypervisor is that management console software is not required. Okay, so the Type 2 hypervisor are very popular with consumers for organizations experimenting with virtualization. So common Type 2 hypervisor includes Virtual PC or the VMware Workstation. You've got the Oracle VirtualBox, VMware Fusion, and the Mac OS X Parallels. Okay, so many of these type 2 hypervisors are free. However, some hypervisors offer more advanced features for a fee. Okay, so note that it is important to make sure that the host machine is robust enough to install and run the virtual machines so that it does not run out of the resources, because everything is shared when you run and use a type 2 hypervisors. Okay, so let's talk about virtual network infrastructure. Okay, so under virtual network infrastructure, we've got the type 1 hypervisor. So in the previous topic, you learned about virtualization. This topic will cover the virtual network infrastructure. All right. So type 1 hypervisors are also called bare metal approach because the hypervisor is installed directly on the hardware. So type 1 hypervisors are usually used on enterprise servers and data center networking devices. So with type 1 hypervisor, the hypervisor is installed directly on the server or network hardware. Then instances of an operating systems are installed on the hypervisor, as shown in the diagram here. Okay, so we have the server, the hardware, hypervisor, OSs are installed directly on the hypervisor. So we don't have a host OS here on the physical device. All right, so with type 1 hypervisor, the hypervisor is installed directly on the server or networking hardware. Then instances of an OS are installed on the hypervisor, as I shown you earlier. Okay, so type 1 hypervisor have direct access to the hardware resources. Therefore, they are more efficient than hosted architectures. So type 1 hypervisors improve scalability, performance, and robustness. How to install a virtual machine on a hypervisor? So when a type 1 hypervisor is installed and the server is rebooted, only basic information is displayed, such as the OS version, the amount of RAM, and the IP addresses. So an OS instance cannot be created from this screen. Type 1 hypervisors require a management console to manage the hypervisor. So management software is used to manage multiple servers using the same hypervisor. So the management console can automatically consolidate servers and power on and off servers as required. Okay, so for example, assume that server 1 in the figure, okay, becomes low on resources. So to make more resources available, the network administrator uses the management console to move the Windows instance to the hypervisor on server 2. All right. So the management console can also be programmed with thresholds that will trigger more automatically. Okay. So it could also trigger the movement of this Windows OS automatically. Okay. Now, the figure here below, okay, the management console provides recovery from hardware failure. So if a server component fails, the management console automatically moves the virtual machine to another server. So the management console for the Cisco Unified Computing System, or UCS Manager, is shown here in the figure. So the Cisco UCS Manager controls multiple servers and manages resources for thousands of virtual machines. So some management consoles also allow server over allocation. Over allocation is when multiple OS instances are installed, but their memory allocation exceeds the total amount of memory that the server has. For example, a server has 16 GB of RAM, but the administrator creates 4 OS instances with 10 GB allocated to each. So this type of overall allocation is a common practice because all 4 OS instances rarely require the full 10 GB of RAM at any one moment. Okay? The complexity of network virtualization. Okay, so how complex virtualization or network virtualization is. So server virtualization hides server resources, such as the number and identity of physical servers, processors, and OSs from server users. So this practice can create problems if the data center is using traditional network architectures. For example, virtual LANs or VLANs used by VMs must be assigned to the same switch port as the physical server running on the hypervisor. However, VMs are movable, and the network administrator must be able to add, drop, or change network resources and profiles. So this process would be manual and time-consuming with additional network switches. So another problem is that traffic flows differ substantially from the traditional client-server model. So typically, a data center has a considerable amount of traffic being exchanged between virtual servers, such as the UCS servers, okay, as shown here in the diagram. All right, so this uses a UCS server. Now, these flows are called east-west traffic, okay, and can change in location and intensity over time. So the north-south traffic occurs between the distribution and the core layers. All right, so you've got the north-south traffic between the core and then the distribution layers. Okay, so north-south traffic occurs between the distribution and the core layer and is typically traffic destined for off-site locations such as another data center, other cloud providers, or the internet. Right? So the east-west traffic is within the UCS servers that is connected to the access layer switches. Next, so let's talk about the complexity of network virtualization. Okay, on dynamic, ever-changing traffic requires a flexible approach on network resource management. Okay, so existing network infrastructure can respond to changing requirements related to the management of traffic flows by using the quality of service or QoS and security level configurations for individual flows. However, in large enterprises using multi-vendor equipment, each time a new virtual machine is enabled, the necessary reconfiguration can be very time-consuming. So the network infrastructure can also benefit from virtualization. So network functions can be virtualized. Each network device can be segmented into multiple virtual devices that operate as independent devices. Examples include sub-interfaces, virtual interfaces, VLANs, and routing tables. So virtualized routing is called virtual routing and forwarding, or VRF. Okay? Now, how is the network virtualized? The answer is found on how a networking device operates using a data plane and control plane, as discussed on the next topic. Let's talk about the software-defined networking now. The previous topic explained virtual network infrastructure. This topic will cover the software-defined networking. So a network device contains the following planes. You've got the control plane and the data plane. Now the control plane, this is typically regarded as the brains of the device. So it is used to make forwarding decisions. The control plane contains layer 2 and layer 3 route forwarding mechanisms such as routing protocol, neighbor tables, and topology tables, IPv4 and IPv6 routing tables, STP, and the ARP table. So information sent to the control plane is processed by the CPU. Now on the data plane, also called the forwarding plane, this plane is typically the switch fabric connecting the various network ports on a device. So the data plane of each device is used to forward traffic flows. Routers and switches use information from the control plane to forward incoming traffic out of the appropriate egress interfaces. So information in the data plane is typically processed by a special data plane processor without the CPU getting involved. Now, illustration and explanation of the difference between the operation of localized control on a layer 3 switch and a centralized controller in SDN follows. Okay, so beginning with the layer 3 switch and CEF, or the Cisco Express Forwarding. Okay, now this figure here illustrates how Cisco Express Forwarding, or CEF, uses the control plane and data plane to process packets. You've got the control plane on top and the data plane at the bottom. Okay? Egress interface, that is where the packet is coming in, and egress interface would be the output or the packets going out. Okay? Now, CEF is an advanced layer 3 IP switching technology that enables forwarding to packets or of packets to occur at the data plane without consulting the control plane. In CEF, the control plane's routing table pre-populates the CEF forwarding information base or FIB table in the data plane. So the control plane's ARP table pre-populates the adjacency table. So packets are then forwarded directly by the data plane based on the information contained in the FIB and adjacency table without needing to consult the information in the control plane. Okay? So the next one is the software-defined networking. Okay, so which is basically the separation of the control plane and data plane. The control plane function is removed from each device and is performed by a centralized controller, as shown in the figure here. Okay, so if you will observe here, if we have different devices, what is left on the device is just the data plane. Now the control plane was removed from this device, okay, and is placed on a centralized controller. Okay, now the centralized controller communicates control plane functions to each device. Each device can now focus on forwarding data while the centralized controller manages data flow, increases security, and provides other services. So the management plane is the plane which is responsible for managing a device through its connection to the network. Network administrators and systems administrators use the applications such as Secure Shell or SSH, the Trivial File Transfer Protocol or TFTP, the Secure FTP, and the Secure Hypertext Transfer Protocol or HTTPS to access the management plane and configure a device. So the management plane is how you have accessed and configured devices in your networking studies. In addition, protocols like Simple Network Management Protocol or SNMP is used in the management plane. So there are two major network architectures that have been developed to support the network virtualization. Okay, so over a decade ago, VMware developed a virtualizing technology that enabled a host OS to support one or more client OSs. Most virtualization technologies are now based on this technology. The transformation of dedicated servers to virtualized servers has been embraced and is rapidly being implemented in data centers and enterprise networks. Okay? Now, the two major network architectures are the software-defined networking or SDN and the Cisco Application-Centric Infrastructure or the ACI. Now, SDN is a network architecture that virtualizes the network, offering a new approach to network administration and management that seeks to simplify and streamline the administration process. Now, the Cisco Application-Centric Infrastructure or ACI, a purpose-built hardware solution for integrating cloud computing and data center management. Now, here are the components of the SDN, okay, so which includes an open flow and open stack with other components. Okay, so open flow, this approach was developed at the Stanford University to manage traffic between routers, switches, wireless access points, and the controller. So the open flow protocol is a basic element in building the SDN solutions. Okay, so search for open flow and Open Networking Foundation for more information on it. Now, the Open Stack, this approach is a virtualization and orchestration platform designed to build scalable cloud environments and provide an IaaS, okay, or IaaS solution. OpenStack is often used with Cisco ACI. Orchestration in networking is the process of automating and provisioning of network components such as servers, storage, switches, routers, and applications. So if you want to learn more about OpenStack, go ahead and search it on the internet. Now, other components include interface to the routing system, or I2RS, transparent interconnection of lots of links, or TRIL. You've got the Cisco Fabric Path, or FP, and the IEEE 802.1AQ, shortest path bridging, or SPB. Okay, so in traditional and SDN architectures, okay, so in traditional router or switch architecture, the control plane and data plane functions occur on the same device. So routing decisions and packet forwarding are the responsibility of the device operating system. So in SDN, or software-defined networking, management of the control plane is moved to a centralized SDN controller. Now the figure compares traditional and the SDN architecture. So on the traditional architecture, if you will observe, we have here 3 devices, and each device combines the control plane and the data plane. Now with the implementation of the SDN architecture, this control plane from the traditional architecture were moved out, okay, and it is now on the same location or centralized location, okay, in this case, the SDN controller, which uses an open flow to manage these devices here. Now, the SDN controller is a logical entity that enables network administrators to manage and dictate how the data plane of switches and routers should handle network traffic. It orchestrates or mediates and facilitates communication between application and the network elements. So the complete SDN framework is shown in the figure. So note the use of application programming interfaces, or APIs, within the SDN framework. Okay? So an API is a set of standard requests or standardized requests that define the proper way for an application to request services from other application. So the SDN controller uses a northbound APIs, got the northbound APIs here, okay, to communicate with the upstream applications. These APIs can help network administrators shape traffic and deploy services. The SDN controller also uses a southbound APIs to define the behavior of the data planes on downstream switches and routers. So OpenFlow is the original and widely implemented southbound API. So next is controller. All right? So SDN controllers and operations. So the previous topic covered SDN. This topic will explain controllers. Now the SDN controllers define the data flows between the centralized control plane and the data planes on individual routers or switches. Okay? Now each flow traveling through the network must first get permission from the SDN controller, which verifies that the communication is permissible according to the network policy. So if the controller allows a flow, it computes a route for the flow to take and add an entry for that flow in each of the switches along the path. So all complex functions are performed by the controller. So the controller populates flow tables. So switch manage the flow tables. So in the figure, the SDN controller communicates with OpenFlow compatible switches using the OpenFlow protocols. Okay, so you've got an OpenFlow switch here, and it uses an OpenFlow protocols to communicate among the switches. Now, this protocol uses a TLS, or the transport layer security, to securely send control plane communications over the network. So each OpenFlow switch connects to other OpenFlow switches. They can also connect to the end user devices that are part of the packet flow. Now, within each switches, a series of tables implemented in hardware or firmware are used to manage the flow of packets through the switch. So to the switch, a flow is a sequence of packets that matches a specific entry in flow table. Now, the three table types shown in the previous figure are as follows. So you've got a flow table, a group table, and a meter table. Now, the flow table, this table matches incoming packets to a particular flow and specifies the functions that are to be performed in the packets. So there are multiple flow tables that operate in the pipeline fashion. Group table, a table may direct a flow to a group table, so which may trigger a variety of actions that affect one or more flows. Meter table, this table triggers a variety of performance-related actions on flow, including the ability to rate, limit the traffic. Okay, so next is the Cisco ACI. So very few organizations actually have the desire or skill to program the network using SDN tools. However, the majority of the organizations want to automate the network, accelerate the application deployments, and align their IT infrastructure to better meet business requirements. So Cisco developed the Application-Centric Infrastructure or ACI to meet these objectives in more advanced and innovative ways than earlier SDN approaches. Now, Cisco ACI is a hardware solution for integrating cloud computing and data center management. So at a high level, the policy element of the network is removed from the data plane. This simplifies the data center networks are created. So there are three components or core components of the ACI architecture, which includes the application network profile or ANP. An ANP is a collection of endpoint groups or EPG, their connections, and the policies that define those connections. The EPGs shown in the figure, such as VLANs, web services, and applications, are just examples. An ANP is often much more complex. So figure on the next slide. Now, the next one is the Application Infrastructure Controller or the APIC. Now, the APIC is considered to be the brains of the ACI architecture. APIC is a centralized software controller that manages and operates a scalable ACI clustered fabric. It is designed for programmability and centralized management. It translates application policies into network programming. Okay, so the last one is the Cisco Nexus 9000 series switches. So these switches provides an application-aware switching fabric and work with APIC to manage the virtual and physical network infrastructure. So the APIC is positioned between the APN and the ACI-enabled devices. Okay, so the APIC translates the application requirements into network configuration to meet those needs, within the network infrastructure. Okay, so next is the spine leaf topology. The Cisco ACI fabric is composed of the APIC and the Cisco Nexus 9000 series switches using a two-tier spine leaf topology as shown in the diagram here. Okay, now the leaf switches always attach to the spines, but they never attach to each other. So similarly, the spine switches only attach to the leaf, and core switches, of course not shown here in the diagram. Now in this two-tier topology, everything is one hop from everything else. So the Cisco APIC and all other devices in the network basically attach to leaf switches. So when compared to SDN, the APIC controller does not manipulate the data path directly. Instead, the APIC centralizes the policy definition and programs the leaf switches to forward traffic based on the defined policies. So the following are the SDN types. So the Cisco Application Policy Infrastructure Controller, the Enterprise Module APIC-EM, extends the ACI aimed at enterprise and campus deployments. So to better understand the APIC-EM, it is helpful to take a broader look at the three types of SDN. So the first one is the device-based SDN. Now, in this type of SDN, the devices are programmable by applications running on the device itself or on a server in the network, as shown in the figure here. Okay, so the Cisco One PK is an example of a device-based SDN. It enables programmers to build applications using C language and Java with Python to integrate and interact with the Cisco devices. So the second type of controller or SDN type is a controller-based SDN. Now, this type of SDN uses a centralized controller that has knowledge of all the devices in this network. Okay. Now, the applications can interface with the controller responsible for managing devices and manipulating traffic flows throughout the network. So the Cisco Open SDN controller is a commercial distribution of OpenDaylight. Okay? So next is a policy-based SDN. Now, this type of SDN is similar to controller-based SDN, where a centralized controller has a view of all the devices in the network, as shown in the diagram here. Okay? Now, policy-based SDN includes an additional policy layer that operates at a higher level of abstraction. So it uses a built-in applications that automate advanced configuration tasks via a guided workflow and user-friendly GUI. So no programming skills are required. The Open or the APIC-EM is an example of this type of SDN. All right. Now, this is an APIC-EM Features. So each type of SDN has its own features and advantages. The policy-based SDN is the most robust, okay, providing a simple mechanism to control and manage policies across the entire network. Now, the Cisco APIC-EM is an example of policy-based SDN. Cisco APIC-EM provides a single interface for network management, including discovering and accessing device and host inventories, viewing the topology as shown here on the diagram. All right, so tracing a path between endpoints and setting policies. Now, the APIC-EM path trace allow the administrator to easily visualize traffic flows and discover any conflicting, duplicate, or shadowed ACL entries. So this tool examines specific ACLs on the path between two end nodes, displaying any potential issues. You can see where any ACLs along the path either permitted or denied your traffic. Okay, so notice how branch router 2, okay, permits all traffic. Okay, the network administrator can now make adjustments if necessary to better filter this traffic. All right, so we have reached the end of this video lecture. Have a great day. See you on the next video.